Alright, this is my lab video for the falling Slinky video for PHYS 2211. To introduce what this is about, we're trying to see if we can create a model computationally that can emulate a gravity-defying Slinky, which I'll elaborate on later on. And we'll use commonly known principles and models like the position versus time graph, Newton's second law of motion, the drag force, Newton's law of gravitation, and also a new concept of the Slinky force, which is similar to a spring, but it's a bit more nuanced. And as a preview of what will happen, we'll see that although our prediction of the Slinky's free fall with drag is a little bit off kilter, the overall modeling of the Slinky's motion is actually quite accurate. Some of our ideas for physics include Newton's second law, which here we can derive the velocity update formula, which says that Vf equals Vi plus F over m times delta t. And in the same sort of direction, the position update formula is Rf equals Ri plus V delta t. Our drag force is given as a simplified formula called F drag equals negative B V squared times V hat, which is the normalized version of the velocity vector. The force of gravity is, Fg equals negative mg times j hat, which is the direction of y. And since the Slinky force equally opposes Fg in the opposite direction, sort of like a tension force, it's equal to F Slinky equals mg times j hat. So it's just a negative version of Fg. And it basically causes the spring to remain stationary because it pulls the bottom of the Slinky upwards to oppose gravity in an equal magnitude. Our experiment details, I used a video of this falling Slinky because I enjoyed watching Veritasium and thought that their video creation would be pretty interesting no matter what it was about. I chose the graph of position versus time because it's really readable, and I chose the formulas for velocity and position update because they're easy to do given F net and delta t, which we know, and drag was used in order to better simulate real life. We assume that the mass doesn't matter because all objects fall in the same manner in a vacuum, so it's just 1 kilogram no matter what. The system is a Slinky and the surroundings are with everything else around it. And the initial conditions include dropping the Slinky from a height of 0.473 meters above the ground as far as its bottom of the Slinky. And also it's dropped without any additional forces, and all else is held constant. And I assume Derek Muller's height to be around 5'9" for the calibration stick to make sure that my spring was correctly calibrated. And to predict the Slinky's motion, I used GlowScript to implement a code version of its falling motion and the position versus time graph as well. And I had 2 while loops here. One was for the part where it was just stationary, and one for when it was actually falling off from the height. So as you can see, here is the code, and the forces at the beginning when it was stationary were just force of gravity and force of tension with the Slinky force. And those are equal to each other in magnitude and cancel each other out because they're in opposite directions and cause it to be stationary. For part 2 though, I had 2 forces as well. I had the gravitational force and also drag to sort of counteract it a little bit, but not fully. So it would fall in free fall motion in part 2 of the while loop. And here's what the graph looks like. It's like horizontal and then turns into a dip motion. And here's the actual display. For the differences, they're very similar in terms of their shape as it goes from horizontal to dipping at the end at a fast polynomial or super polynomial rate even. And the actual graph dips at a faster rate than the predicted graph by just a little bit, which is due to other factors that we didn't account for. For potential errors, it was hard to track the Slinky's position on tracker because the video quality was kind of crappy, and therefore it's hard to see the Slinky at certain times throughout the video. Therefore, the observed graph is very jagged in comparison to what it should be, which is a lot smoother in an ideal world. Our model is also too simple and didn't account for other forces that cause fluctuations and nuances in the real video's motion, things that are beyond the complexity of just drag and gravitational force. As for our discussion questions, why does the bottom of the Slinky remain stationary? It's because of the propagation of forces throughout the spring, and thus because it's a spring-like object, it has an upward tension force from the top of the Slinky that is equal and opposite to the gravitational force, and that keeps happening, keeps causing the stationary until it fully falls from top to bottom. And then if we attach a similar object like a tennis ball or even a shoe to the bottom of Slinky, it'll still have the same exact motion where it'll keep being stationary until the top reaches the bottom, and then it'll fall down together because the force no longer has tension to it. And that will be all for my video today. Thank you for watching, and this is the very last video in PHYS 2211 for my lab report, and I'll see you guys next year in Physics 2. Alright, goodbye.